So we'll move on to our next speaker, Joy Xu, a PhD candidate in computer science at Stanford. Joy's research focuses on multimodal understanding and reasoning. She's a Knight Hennessy Scholar and an NSF graduate research fellow. Joy, the floor is yours.
Perfect. Thank you for the very kind intro. My name is Joy, and today I'm very excited to talk about my work on building neuro-symbolic multimodal systems for science. So let's first talk about multimodal reasoning. We've seen great success in the field in the past few years. There's models now where I can pass in an image in a query and understand how many gallons of gas I can afford, or where this beautiful campus is. But while multimodal reasoning has really advanced in the past few years, it is still not being broadly used in critical real-world and scientific settings. For example, in the real world, we may have millions of remote sensing imagery, and we may be asked to understand what are the underlying rules of land use. Or we may have a recording of neuroactivity from a participant, and we'd be asked to decode the complex visual stimuli that the participant is viewing. And so while these settings are highly impactful, they come with their corresponding challenges. First, they are typically in data-scarce domains, which means there's very little labeled data. At the same time, it also consists of really complex reasoning tasks. So I propose that we should build generalist multimodal systems that can solve such complex tasks in data-scarce domains. And moreover, I argue that monolithic models tend to struggle, because the scarcity of data in these domains, paired with a combinatorial explosion of possible subtasks chained together, makes exhaustive supervision infeasible. And hence, these end-to-end monolithic models tend to suffer. In contrast, I propose neuro-symbolic concept-based systems that uses the underlying structure of the task and the physical and natural world in order to reason about these problems in an efficient and generalizable way. I'll show that this allows us to solve these real-world scientific settings we've just seen, as well as a variety of complex tasks in data-scarce domains. And so today in my talk, I really want to talk a bit about how we've been thinking about neuro-symbolic concepts and how they can form multimodal reasoning systems. And I want to motivate this by talking about the concept left. So what does left mean? Well, in 2D, you can find a large sphere to the left of the red sphere. In 3D, you can face the cabinets and find the object to its left. In robotics, you can pick up the toy on the left of the other ones. And in the temporal domain, you may find that a person has moved left from a base frame. So the single concept left has groundings across all of these domains. But the concept symbol itself serves as a basis for complex and multi-step reasoning. For example, we can use a large language model to reason about these concepts, about how they compose and how we can resolve them to solve a variety of tasks. And so really, from this framework, we have kind of defined a set of works on neuro-symbolic learning, which at a high level uses neural networks where the world is continuous and messy, and uses symbols where precision and composition really matters. And so here I want to highlight a work called Logic Enhanced Foundation Model, which is also aptly titled LEFT. And the idea behind LEFT is really that it uses domain-specific concept grounding modules as neural networks that are fully differentiable, paired with domain-independent reasoning done with symbols through, for example, a large language model. So let's talk through how this actually works. Suppose we're given an input visual query, here a 3D scene, as well as a language query, like facing the blackboard, find the relation between the black chair and the blackboard. Well, we can first use a neural network to extract entity-centric encodings of the scene. These means features for each object in the scene, each pair of objects forming relations, and so on. At the same time, we can use a large language model to parse the underlying program from this task that tells us how we should reason about this affirmation task. Then we can conduct neuro-symbolic learning, which is essentially using these programs to tell us and guide us on how we should compose these concepts and object features to solve tasks. Now, importantly, our neuro-symbolic learning systems are fully differentiable, which allows us to learn in domains where there are not pre-trained models. For example, in remote sensing or in neuroscience. So now once we have this program, we can very easily extract underlying subroutines, which then optionally call upon concepts like blackboard or black chair. Then we can take these learned object-centric features from the scene, for example, each value here representing an object in the scene, and simply apply a concept neural network to tell us the probability that each object in the scene is possibly a blackboard. We can do the exact same for all possible chairs in the scene, as well as all possible black objects in the scene. And now to find a black chair, we can simply apply a differentiable min function to find what are possible black chairs in the scene. And now these two object sets, paired with our learned features of relations between objects in the scene, can allow us to predict the correct relation left. And this full execution can be done really simply using the soft summation we see here, which is essentially a weighted sum over all possible pairwise embeddings where the weights reflect the neural network's estimated likelihood that object X is a blackboard and object Y is a black chair. Now, the really cool thing is that this allows us to do end-to-end differentiable programming through the entire system without explicit constant notations. Our gradients not only backpropagate through the concept neural networks, but through the original neural networks that produce these object-centric features in the first place. So in this paper, we show that we can apply the same differentiable neuro-symbolic concept learning framework across the 2D scenes, 3D indoor scenes, 4D temporal human motion, as well as robotic manipulation. And it allows us to solve complex tasks across all of these diverse visual domains. But importantly, left is also incredibly data efficient. So here's the performance of left in the 3D domain with very, very little trained data. And we see that we significantly outperform all prior works based on transformer-based models. At the same time, left also generalizes well to unseen tasks. Left is again here in pink. And that is because we can, at inference time, dynamically compose these concept neural networks as needed to solve a wide range of tasks without ever seeing that combination or length during training. But also importantly, left is also easily adaptable across different settings. So here we have some really exciting ongoing work that applies left to the remote sensing domain, where the input is millions of remote sensing imagery, and the goal is to create a system that is not only accurate, but it's incredibly efficient at inference such that we can parse through these millions of images captured by satellites. So we see here left, also in pink here, is not only accurate, but it's incredibly efficient because the concept neural networks we've just seen can be as large vision language models, but also as small as MLPs. And that allows us to do really efficient inference. And we also have recent work that applies left for neurodecoding. So here, the input is an fMRI recording of participants. And the output is forced to decode complex concepts that existed when the participants viewed visual stimulus. And because left can compositionally generalize very well, we see that left, here also in pink, significantly outperforms all prior neurodecoding works on this task. So to summarize, I'm super excited about left as a framework for multimodal reasoning that is not only efficient and generalizable, but also precise and interpretable. We see that it works really well in these data scarce domains across complex tasks, which are also very prevalent in scientific domains. And I'm excited about continued work in this field. Thank you. I'm happy to take any questions.
I'll first ask a question while waiting for others if there's any. So it seems like these neuro-symbolic models are gaining a lot of popularities and attention right now, and it's very applicable to different domains. Do you see any limitations or challenges we need to go over in order to make it actually applicable to like various general domains that we use more black box neural networks for now?
Yes, I think you've gotten that feedback a lot, and thanks for the great question. One thing that these large, like end-to-end monolithic models are really good at is learning spurious correlations. And you may think all spurious correlations are not great, but actually there's a lot of spurious correlations in the data sets we're testing on. For example, in a lot of 3D domains, there's a lot of co-occurrence of, say, chairs connected to tables, right? And so this co-occurrence that exists, if these end-to-end models can learn these spurious correlations, they actually do better on these specific tasks. And so I do think that like if your domain is really constrained and you know these correlations exist, then these end-to-end attention-based networks will do quite well. But if you really care about a generalist model that can be applied to any setting and solve any task, I think that's really where neuro-symbolic learning shines.
Thank you.
Our next speaker is Simran Khanuja, a PhD student at Language Technologies Institute at Carnegie Mellon. Her research expands the capabilities of multimodal systems to serve diverse users across languages and cultures. She has presented award-winning work at top venues like EMNLP, and she's a Weibo Presidential Fellow. Please join me in welcoming Simran.
Thank you so much. I'm Simran, I'm a PhD student at CMU, and today I'll be talking about my research on machine translation for vision. A lot of the work that I do is not very closely related to AI for science, but today I thought that I'll think about some fundamental problems that exist across my research and AI for science, and I will be talking about two such problems. Joy talked about low resource issues, which I commonly face in my research, so that'll be one of the main themes. Brief agenda, I'll motivate my problem, I'll give a very brief overview of 3 of my works, and I'll finally conclude. So, what is machine translation for vision, you might be wondering? When we think of machine translation, we usually ask the question, okay, which language do you want to translate into or from? But when I was working with this organization a few years ago, they had these storybooks for children, and these stories were highly illustrative. They had images and text, and the illustrators were from India and Africa. And the issue they faced is that they had translated all of the text from these stories into different languages, like European languages, but very few people were reading these stories in those languages. And the issue was that the images need to be recontextualized to the cultures which they are translating these stories into, right? A child reading the story in Spain may not be able to relate to this woman as their grandmother. And what we realized when we try to dive deeper into the problem, we saw that it actually exists in multiple domains. So in movie adaptations, we see that a lot of visual elements are changed across countries. We see this in education, where teaching a child concepts using objects they see in their daily surroundings is very important. It aids learning. And obviously, we see this in ads, because you need to sell your product in different markets, and you want to make it as, incentivize them as much as you can. So the first work that we did, we presented it at EMNLP, and the main challenge there was how to sort of operationalize this problem that exists in the real world for machine learning research. And my approach typically when I look at a new task is we first need to build a very challenging test set, or a test set which sort of emulates real world needs, because evaluation is what drives progress, right? So we built like a very simple test set. We collected images across different countries and different domains, and our task was really simple. If we have this input image and we want to make it more relevant to a target culture, we basically just test for whether the final output is, more relevant to the target. And also it should just belong to the same category that the input was from. So a food image should not change into like a house or something, which does happen, by the way. So once we built like this test set, we thought, okay, let's test what our SOTA image editing models can do. And this is the first model that we tried. This was around 2 years ago, and Instruct Pix to Pix was like the most famous model at the time. So it can do simple things like object swapping, style transfer, but really its sell was it can, understand abstract natural language instructions. And when I put it to test, when I said, okay, make this image culturally relevant to India or Japan or Turkey, these are the input images, I found very unnatural looking outputs. So India was all about gold, jewelry, randomly placed. They follow the shapes and edges, as you can see, but the pixels will be filled with what they think is India or Japan. In Turkey, I saw this word sense disambiguation problem where it looks at Turkey as Turkey the bird, not Turkey the country. And any guesses what this might be? It's very easy. Okay, it's the US. It's like blue and red, white stars. Yeah, so clearly image editing models are not very good at understanding language. So we thought, okay, let's make LLMs do this heavy lifting of cultural translation, right? So we sort of caption the images. We ask an LLM to edit it for cultural relevance, to make it culturally relevant, and then we give these image editing models very concrete instructions, like change the links to a tiger. And it seems to work decently well. Another thing we tried was, instead of editing the original image, can we retrieve a natural image from the internet, given our LLM edited caption? And this was because of some limitations that we saw with the previous pipeline. But even with all of these different things that we tried, we could only successfully transcreate around 5% of the images for some countries. And we also created a test set directly from real-world images, like from ads and education. And for that, we didn't see any success for, say, Portugal. And so one thing we realized is that, OK, we don't have good eval metrics, we don't have good models, we don't have good data. And I was like, OK, if we need to make progress here, the first thing we need to do is think about how we can build automatic evaluation metrics for this task, because human evaluation was very costly, and people won't really work on this problem unless they have like this number that they can optimize, right? So when I tried using simple vision language models like Quen and asked it, OK, which cultures is this image relevant to, right? This is the response that I get. And there are two problems with this. One is VLM sort of assume a definition of culture. Culture can also just be residents of Manhattan versus Brooklyn, for example, right? So the user should be able to define culture the way they want to. And the other problem is that the models were not being able to recognize these entities. Like it gave a very generic response, but this is actually an entity which is culturally salient in certain parts of the world. So the way we try to solve this problem is we built this tool. It's called CARE. We can upload an image here, and we let the user define how they want to define culture using natural language text. So they can give country names, they can give religions, they can give different states of Mexico. We let them choose which model they want to use. And what we do at the back end really is find like best matches from Wikipedia for that image using certain image text matching techniques. And once we have all these Wikipedia pages retrieved, we use like a Quen model to sort of do VLM scoring, and we get this sort of output, like a different cultural relevance score for each of the user-defined cultures. And we can also like look at the reasoning, which the model gave for the different scores that it assigns. So this is one way in which we try to tackle this low resource problem by augmenting with offline knowledge bases and really giving users as much control as possible in defining these sort of nuanced concepts, right? The second work that we did was, OK, now we have a decently good enough evaluation metric. And I was thinking that, especially looking at this model, right, instruct pix to pix, it was not good. But it can do certain things well. And then I saw that, OK, there are so many other models which are highly specialized at doing very specific things. Like there's a model which changes orientation of objects. There's a model which can replace objects with a reference image and so on. And I thought that AI models lack semantic understanding of culture, but they are technically efficient at following very specific instructions. Humans may lack technical skills to make quick edits, but they are highly proficient in nuanced cultural understanding. Like, there are so many translators, they know so much about different cultures, but they may not have these graphic designing skills, right? So why don't we combine the two? So this is another platform we built. I'll just show you very quickly, where we let the user input or upload an image. We let them We ask them to give like a very simple natural language instruction. We let them choose certain hyperparameters. We run multiple diffusion models at the back end because we never know which one might give us a good output. And then once we have different outputs, we let the user sort of select which one they like out of like 6 images. They can rate how they like it on multiple criteria. And then they can sort of continue editing the image on the platform. So this is like step 1, and then they can continue editing until like, they're satisfied with the output. So this is the platform we built. We did some human collection, like a collection with translators. And these are some of the creations we had. The top images are input images, and these are some outputs that we got using the platform that we built. Yeah, in conclusion, sorry, I may have gone too fast. But in summary, I just wanted to talk about the new task that we introduced in our paper 2 years ago. And I spoke about how current SOTA models fail at this task. And to tackle some issues in this domain, we've done some work on trying to combine offline knowledge bases, trying to give users as much control as possible through both of our works. And yeah, thank you so much. Just to note that I'm really excited about this problem. So if any of this interests you, please feel free to reach out now or later. Yeah, thank you.
Our final speaker for this session is Giannis Daras. He's a postdoctoral researcher at MIT, working with Professor Kostis Zaskalakis and Antonio Torralba. He earned his PhD at the University of Texas, Austin, and his work explores deep generative models and has been recognized with oral and spotlight presentations at Neurips. So once everything is set up, the floor will be yours.
Perfect. Okay, let's get started. I'm Giannis Daras, and today we're going to talk about generative models. But there's going to be a twist. Okay, so here's the twist. The twist is that we are going to be training these generative models with bad data. So we are going to be thinking about how can we train these models when we don't have good samples, but the samples are corrupted in some sense. And by the end of this talk, I want to convince you that this is a very important problem. Maybe you should work on it, and especially for applications in science. And okay, let's see. Okay, perfect. So instead of talking about a single paper, for this talk, I kind of decided to give you like a sense of the overall direction. This is what has been keeping me busy for the past 2 years. So I'm really thinking about this problem, and we have applied in a bunch of different domains, from like computer vision to computational biology, neuroscience, robotics, and so on. So without further ado, let's get started. So the first chapter of this talk is going to be about the power of bad data. So to get started, I want to show you an example. So as I'm talking, I'm showing you this like image that has been corrupted in a very particular way. So someone got there and added a lot of noise to this image, right? So as I'm speaking, I want you to think like, how much can you tell from this sample? If I give you this image, what do you think is behind it? I would argue that it's going to be really, really hard to tell that this is an image of me posing for a photo in Boston. Maybe you can tell that there is a person. Maybe you can tell, like, I don't know, maybe you can tell the silhouette. But it's going to be really, really hard to think about like what is actually there or find the details, because the image that I gave you is corrupted. And maybe I can even make it like much, much harder. So I give you this other image that has been corrupted in another way. 99% of the pixels are missing. So the only thing that you see is like 1% of pixels, some like dust of white pixels there. So you can't really tell much. But the underlying image is, again, like another person. And it's really, really hard to guess it from the image I gave you. So this discussion paints a picture that basically says that these like bad samples are kind of useless. You cannot tell much. They do not convey a lot of information about like the underlying distribution. But here is the surprising thing, okay? What if I told you that there is an algorithm that only sees these bad samples, but sees a lot of them? So it is trained with a lot of pixels, a lot of images that most of their pixels are missing. And after training, this algorithm can actually generate like faces that have no corruption at all. It can model the underlying distribution without ever seeing like a clean sample. So the pipeline is actually like really simple. You have some training data, And then you have a diffusion-like algorithm. Diffusion is the dominant paradigm in like learning high-dimensional continuous distributions. And at the end of it, you have a generative model that knows how to generate images without ever like seeing one. And there is nothing really particular to this masking corruption. You can actually do it with other types of corruptions as well. So in these other papers, we have a model that is a text-to-image model, has never seen a clean image. Only thing that has seen is this like data that they look like garbage. They have been corrupted with like additive Gaussian noise. Yet this model can actually pretty decently generate some images. Of course, it's very far from state of the art, but you would think that it would be really, really hard to generate like samples from these like bad data, but yet it is actually possible to do it. So the message here is sometimes, even though it might be counterintuitive, at least practically, you can learn how to produce samples from a distribution without ever observing a clean sample. And there are also some theoretical guarantees about it as well. But I don't want to like waste my time on that. I want to like now convince you that like now that we know that it's sometimes possible, why is that a good problem, right? Like why would we care about this problem? Why do we want to like we have good data sometimes, so why do we want to like learn models from this bad data? And it is important for like 3 reasons. And I want to start by saying that we are like so addicted to having access to these large-scale, high-quality data sets that we sometimes don't think that in like a lot of these applications that we care about, these scientific applications, we have like data scarcity, so we don't have a lot of data, right? So when you don't have a lot of data, you actually cannot afford to have like these big data sets, and you have to train with like limited samples in science. And when you train with limited samples, a lot of problems arise. One of them is that your models memorize a lot. And then that is a problem. So maybe in these particular settings, training under corruption can give you a way of having models that generalize better. But even if we are to talk about these like very data-rich domains, like these image-text generative models, I would then argue that, again, it is very problematic to be throwing out these bad samples. The reason is that the data sets that we have, when we collect these large-scale data sets, they have a lot of bad samples that people like tend to filter out. And they do this because they want to have these impressive demos, right? So you want to have like ChatGPT that whenever you say, give me an image of like a person doing that, the image that you get are amazing. So in that process, you want to filter out like all of these low-quality images. But the danger there is that you might be biasing your distribution. You might be creating like these like biases that you're not even aware of. For example, most of the low-quality images are taken like during the night because the camera sensors work less good like in this particular setting. So if you do this, if you filter out this bad quality image based just on quality, you might end up with like a generator that does not produce images during the night. Cool. So hopefully I convinced you that this is important. So now I will give you a little bit like my thinking about this problem. And I don't want to delve into like all of these technical details too much, but I want to give you like the recipe, okay? So if you give me like, if you tell me, oh, Giannis, I want to train a model like from corrupted data in this particular domain, and I want to like use either diffusion or autoregressive models, I will tell you how I think about it. And I think about it in 3 steps. The very first step is I'm taking a leap of faith. So I'm saying, okay, what if your corruption is actually simple? Can we learn to reverse this? Can we learn to produce like clean samples without ever like seeing one? But the corruption has to be simple, right? So for example, in the context of diffusion models, I already showed you some results where we trained models with like noisy images, and they were still able to produce clean images. So how would that work? Usually in diffusion, you have this model that is trained as a denoiser, so you see a noisy image and you predict a clean one. But it turns out that like if your corruption is actually like simple enough, you can devise a new loss function that does not involve like clean images, but it can still like learn the same minimizer. So the fact that your corruption is simple actually allows you to be doing this like simple stuff and develop this like nice math that has these nice properties. But I hear you. You tell me like for the application that I wanna use it for, the data is actually not corrupted in a very like simple way, but we have like these arbitrary corruptions. The images are like blurry, they have compression, they have this, they have that. So what do we do there? And we do something like counterintuitive. And I want to show you this with a little game. So what we do is we actually corrupt them further to make it look like something that we can analyze. So here we have like 2 images. One of them is like blurry and one of them is clean. And we want to see what happens as we start adding noise, right? I start adding noise to both of these images, and we want to guess which one is which. And as you can see, like the more you add noise, the more trickier it becomes to tell which one is which. So there is a point, there is a level of noise at which like the clean image plus noise and the blurry image plus noise, they have kind of merged. So you can maybe like use the blurry images plus noise as clean image plus noise and revert back to this like previous framework. Okay, now time for some results. When you do this, you actually get like a very big boost in quality without sacrificing any diversity. From models trained on computer vision, like in datasets like ImageNet, you see like some examples on the left for baseline and the right for our method. And then it goes to some dramatic improvements when you do text to image. So I'm going to close with my favorite application in science. So we have been thinking a lot about how do we do these things for science. So I'm going to tell you like my favorite application. My favorite application is proteins. So you want to generate protein structures. But here is the problem. Each sample costs a PhD. So someone needs to spend like 5 years crystallizing the protein, solving the inverse problem of going like from the diffraction patterns to the protein, and this is like really, really costly, right? So we don't have a lot of data, and if we naively train on this data, we just like cannot get good models. So what do people do? They generate data from AlphaFold. They generate synthetic data, and they train on that. But this synthetic data, they have corruptions, and that leads to models that do not perform well when the protein is large or when the protein is complex. So what we do in this work, we just treat like synthetic data as noisy data, and we just apply this idea of adding noise to view them as clean samples, as real proteins plus noise. And that leads to very big improvements in both diversity, so we're generating novel structures that have not been seen before, but also in quality. And these improvements become more pronounced the bigger and the more complex the protein becomes. So with that, I'll finish my talk. Thanks so much, and I'm ready to hear your questions.